Equilibrium is important, and I use the example of ammonia here. You've seen the equation. There was originally a dilemma. How can it be economically produced? Well, industry uses experimental design where people first started in the lab to look at different temperatures and pressures, and it was scaled up along the way in order to come up with a temperature pressure system which economically produced it. And it is a $28 billion industry. So where we're going to begin? Well, we're going to show how do you work with equilibrium concentrations given different pieces of information. Here we have an equation for PCl3 where it says 0.16 mole and it says 0.25 moles and it says this is at equilibrium. It wants to know what is the concentration of Cl2. Well, based on what you know so far, we could say here's our product, here are our reactants, and let's see what we know. Well, it says a 1 liter container. That means this is 0.16 molar, this is 0.25 molar. So I can put in 0.25 molar, I can put in 0.16 molar, and my equilibrium constant is given as 1.9. If I rearrange this, and I'll go slower in our lecture Zoom, 0.25 divided by 1.9 times 0.16, it's going to give me the numerical value of 0.82 molar. That's our first example. Our second example in this system is to talk about Kc and Kp. Same equation, we're given the Kc in this case, we're asked for the Kp. So what we'll say is we'll say Kp is equal to our Kc, 0.040. We'll multiply it by R, 0.080206. We'll multiply the R by temperature in Kelvin, which is 473. And now we need our delta N, which is our moles of product minus our moles of reactant. Products we have 2, 1 plus 1. Reactants we have 1. So this is raised to the first power. Raising this to the first power gives us a Kp of 1.6, all right? Very straightforward. What I want to bring your attention to, whenever you have to do a Kp calculation, always do your delta N. I have 3 in terms of my moles of product, and here I have 1 plus 2, and I come up with a 3 minus 3 equals 0. That says I'll be raising RT to the 0 power, which is equal to 1. And in that case, Kc is equal to Kp. Please do some problems because these are a lot more complicated. That brings us to transitioning you to from a BCA to an ICE table. Prior to starting this, what I did is I worked out as many numbers as I could. It says you have 2 moles of X and 2 moles of Y in a 4 liter container. So what I did is I found, because equilibrium constants require molarity, we have 0.5 of X, we have 0.5 of Y, and we have no Z whatsoever. Something you haven't worked with before. They're telling us the equilibrium concentration of X is 0.3. What does that mean? Well, remember, when you did a BCA table, you added those numbers together or you did your algebraic operation. Here, if I subtract 0.2, I am going to get a 0.3. And for this example, it is a 1 to 2 to 3 ratio, a 1, a 2 to a 3 ratio. So if I use 0.2, I am going to have to use 0.4 of Y. I am going to produce 0.6 of Z. So I'm going through this quickly. I will go through it slower in lecture Zoom, but again, it is an example. What's my equilibrium constant? Well, it is Z cubed times divided by X times Y squared. So I have 0.6 cubed times my X times my Y squared. This is a typical midterm problem. I realize I went through it quickly. I will go through it slower in lecture Zoom. X, finally, this I've practiced over and over. This is like the 6th tape of this YouTube video. This is where you're going to start to use variables. And not really variables, but we're going to think through this one because variables come next. This is sample exercise 15.8, where you are given an equation. You are told there is this amount of hydrogen gas, this amount of iodine gas. You're given the equilibrium, you're trying to find the equilibrium constant K, and they're telling you the concentration of HI at equilibrium is 1.87 times 10 to the minus 3. So let us get started. We want to tabulate the known information. So that's what I did here. There's my equation. I put the values in that were given in the problem. The big change is we've now been given an equilibrium product calculation. That's why I did that first example. Numerically, these have to combine in order to come up with our equilibrium calculation, concentration. So it says we have to add in 00187. So what are you going to do now? Well, you're going to use stoichiometry to calculate those changes, and you're going to complete that table. And that's what I've done on the next 2 slides. So here is a repeat of the slide, and what I should have done is put in my 00187. I'm going to use that number in order to come up with these. Now, you may have said, I can do this in my head. Well, I wasn't sure everybody could. So I want to say that change line is determined by stoichiometry. I know it's 1 mole of H2 for every 2 moles of HI. That gives me my numerical value of H2. I know it's 1 mole of I2 for every 2 moles of HI. That gives me my numerical value for I2. I just did not want to say 1 to 1 to 2 because you're going to get a lot of different problems where these are going to vary, and you do need to do this calculation. So since this is complicated, I repeated it one more time. Here I have my values placed into the table, and what we have are our equilibrium numbers. Again, long problem. I repeated my equation, I repeated my K, and what I'm going to do now is I'm going to put my values in that have been determined from the ICE table. We're going to be going to variables in the next section. So if this was a little bit confusing, please take time here and work everything out so you're confident in this process. It's a tough one. So good luck, try, ask questions.